Today's session will discuss an example of a complete analysis of an amplifier using an H parameters, followed with approximate analysis of an amplifier using H parameters. For example, the transistor amplifier shown in figure uses a silicon transistor with VCC 24 volts, RS 1 kilo ohm, R1 100 kilo ohms, R2 10 kilo ohms, RC 2 kilo ohms and RE 470 ohms. Calculate various gains and input impedance and output impedance using H parameters. One way of doing is this: you have to write an equivalent circuit of a transistor amplifier and then you have to analyze. First, let us consider an equivalent circuit of an amplifier. Replace transistor with its equivalent circuit, that is HIE, with a constant voltage source HRE, VCE, a constant current source HFE times IB is followed with a HOE, and then this is the collector, emitter, base. For this circuit, you have to transfer the external components. In this transistor figure, that resistance RE is in parallel with CE. This at the low frequency, that capacitance is acting as a short circuit, and then RE is short circuit. To transfer that remaining components, you have to set VCC is equal to 0. Then that resistance RC is connecting between this point, and then collector current IC, and then this current is IB. And similarly, you have to transfer the resistance R1, R2 and RS into the circuit. When set VCC is equal to 0, already that base is resistance R2 is connecting to the emitter, R1 is also connecting to the emitter in parallel with, then there is a series resistance RS is followed with Vs. In the previous circuit, this and collector circuits, and then we have to, this output is to be taken across this point, and then input is applied between this point. Then we can replace VCE with V0. Okay, that current flowing through this is given by II, and output current is flowing opposite to that, that is given by I0. Already we know that for this circuit analysis, we determined that input impedance, we are looking into the terminal, a base emitter junction, that denoted with Zi. When you are looking into the resistance R1 and R2, this resistance is denoted with Zi dash. Similarly, when you are looking into this with RC is equal to 0 infinity, then this is Z0. When you are looking into this point, this resistance is Z0 dash. That various current gains and input impedance means we need to determine the voltage gain AI is equal to I0 by IB. This I0 by IB, then this current is to be, already we know that this formula for this is minus HFE divided by 1 plus HOE into RC, where that ZL is equal to RC in this case. This, if you substituting this values, where HFE is given by 50 minus 50 divided by 1 plus HOE is 24 into 10 to the power of minus 6 into RC is given as 2 kilo ohm, 2 into 10 to the power of 3. If you are simplifying this equation, you are going to get the value gain of the amplifier is equal to minus 47.7. If you use, because once we know the value of AI, we will get that input impedance Zi, where input impedance Zi is equal to HIE minus, plus AI HRE into RC. This, if you substituting this value, HIE is 1.1 K, that is 1100 ohms, plus AI is minus 47.7, HRE is 2.5 into 10 to the power of minus 4, and RC is 2 into 10 to the power of 3. If you are simplifying this, you are going to get the value is 1077 ohms. This impedance is, we are looking into the base and the emitter terminal. In this case, if this transistor is a voltage divider biasing amplifier, then you have to determine the actual input impedance. If you are considering that resistance R1 and R2 into the account, then this Zi dash is a parallel combination of Zi is in parallel with R1 is in parallel with R2. This is nothing but 1.007 is in parallel with 100 is in parallel with 10 into kilo ohms. If you are simplifying this, you are going to get the value is approximately 957 ohms. Means if you are this implies that when that biasing resistances or due to the biasing resistances, its input impedance is further reduced in case of a transistor amplifier. Next, we need to calculate a voltage gain AB. Voltage gain AB is given by AI into RC by Zi dash, because due to the you have to consider to determine the voltage gain of an amplifier, you have to consider the biasing resistances. Instead of Zi, you have to use a Zi dash. If you are substituting this value minus 47.7 into 2 into 10 to the power of 3 divided by 957 ohms, this value is approximately equal to minus 88.58. Next, output impedance Z0 is equal to 1 by Y0, where Y0 is given by, because when you are calculating the Z0, you have to open circuited load resistance and a short circuited input voltage Vs. According to this, you are going to get this HOE minus HFE HRE divided by RS plus HI. The input source resistance of an amplifier is given as 1 kilo ohm. Then if you substitute this value 24 into 10 to the power of minus 6 minus HFE is 50, HRE is 2.4 into 10 to the power of minus 4 divided by RS is 1 into 10 to the power of 3 means 1000 plus HI is 1100. This value leads to 20.96 microsiemens or mho. Then Z0 is equal to 47.69 kilo ohms. It is a reciprocal of that Y0. If you are finding this various gains, this is with respect to the transistor amplifier without considering that source resistance RS and the external components RC. To determine the voltage gain and current gain while considering a source resistance RS into the account and a load resistance RC into the account. From this circuit, Z0 dash is defined as, when you are looking into this at collector emitter terminal, that resistance, this complete amplifier is replaced with Z0, then the Z0 dash is a parallel combination of Z0 and RC. This is nothing but 47.69 kilo ohm is in parallel with 2 kilo ohm value. This is approximately you are going to get a 1.9 kilo ohms. If you are considering that a output impedance Z0 dash and a source RS, then that gain of the amplifier, current gain of the amplifier is also varies and voltage gain of the amplifier is also varies, where a current gain of the amplifier with a source resistance RS into the account, then it is denoted with AIS. This is equal to AI into a voltage drop across, means current flowing through this is nothing but RS divided by RS plus Zi dash, because you have to considering R1 and R2 into the account. If you are substituting this value minus 47.7 into 1 into 10 to the power of 3 divided by 1000 plus 957 ohms, this value is approximately equal to minus 24.37. Means if you consider the source resistance into the account, the gain of the current gain of the amplifier is further reduces to that. Means if the value of this RS is higher the value, then the gain is also higher. But for a current source, this resistance RS is to be a smaller smaller. Then we need to calculate a voltage gain. If they ask you to calculate a V naught by Vs, if you want to calculate, because this AV is the ratio of a V naught by Vi, means we need to calculate the what is the voltage at this point due to the effect of that R1, R2 and Rs. Then this is equal to AV into Zi dash divided by Rs plus Zi dash, because with this complete, when you are looking into this, the entire amplifier is replaced with a Zi dash, then this source is to be becomes Rs into multiplied with Zi dash, this is your Vs. The voltage up across this is nothing but a Vi. Hence, this value is given by this. This is equal to minus 88.58 into Zi dash is 957 ohms, Rs is 1000 plus 957. The gain of the amplifier is equal to minus 43.31. From this example, we conclude due to the effect of that sources Rs and R1 and R2, parallel combination of R1 and R2 biasing resistances, the gain of the amplifier, current gain and voltage gain both are decreases, and also the input impedance is also reduced to the from 1077 ohms to a 957 ohms. Next, let us consider an approximate analysis. For the approximate analysis, under what condition we are going to approximate the exact analysis, and what is the acceptable error? If you answer to these questions, then this circuit analysis is to be further reduced to a simplified version. Means the condition for a approximate analysis is HOE into RL should be less than much less than 1, because we know that a current gain AI is given by a minus HFE divided by 1 plus HOE into RL. If this value HOE into RL is much smaller than 1, this implies that you have to remove this inequality sign by substituting that HOE into RL is approximately equal to 0.1, means or 1 divided by 10. The minimum condition for this removing an inequality sign is nothing but a 0.1, means if that HOE into RL is less than or equal to 0.1, then that error between the exact analysis and approximate analysis is less than 10%. Means that 10% tolerance means error is acceptable for the analysis of a small signal amplifier. Then if this condition is satisfied, HOE into RL, means in this case that RL is nothing but RC, that HOE into RL is satisfying that less than 1, then this equivalent means we have to neglect that value HOE and HRE, because HOE is the value is a 25 into 10 to the power of minus 6 mhos, and HRE is defined as 2.4 into 10 to the power of minus 24 into 10 to the power of minus 4, 2.5 into 10 to the power of minus 4. These values are negligibly small, then this equivalent model is to be rewritten as from the base and a emitter, the only resistance is existing, this is HIE, the current flowing through this is nothing but IB, and the output side this HOE, this conductance is also a smaller value, then the resistance is large, then we can neglect this value, then the output side only a constant current source, that is nothing but HFE into IB. Current flowing through this is IC, this is C and then this is E. Means instead of using in an approximate analysis, instead of using this equivalent circuit, you have to simplify the hybrid model into the as shown in this figure. Then you have to replace transistor with this equivalent circuit, then the error is less than 10%. That is the one point. If using this, then that a complexity, that analysis, doing the analysis, that complexity is also reduced. Now next question arises, then what is the difference between the RE model and hybrid model, approximate hybrid model? For this case, answer is, we know that already that RE model is defined as, for a common emitter amplifier shown here, this is beta times RE, current flowing through this is IB, and a current source is given by beta times IB, current is IC. If you are observing this two circuits, RE model and a approximate hybrid model or a simplified hybrid model, that a resistance HIE is equal to beta times RE and a beta is equal to HFE, where HFE is the a short circuited current gain, where beta is nothing but the ratio of that collector current to the base current IB. Another important thing is HI is equal to beta times RE at IC is equal to 1.3 milliamperes and temperature is constant. This HIE is also constant. What about this beta times RE? Because if the temperature is constant, beta is also constant, but this RE is depends on the transistor current flowing through the circuit, because the transistor current, and then also is depends on the external biasing resistance. This is one of the drawback in case of an RE model. If this model is valid, then the analysis of a RE model and a simplified hybrid model or a approximate hybrid model are equal. Using this, this is the a comparison of differences between the RE model and the simplified hybrid model. Using this simplified RE model or a hybrid model approximate analysis, we are going to discuss in detail a fixed bias, a common emitter amplifier, a voltage bias, divider bias, a common emitter amplifier and an emitter follower. Now let us consider the first case, a fixed bias circuit. The circuit shown in that fixed bias circuit the transistor is replaced with the simplified hybrid model. For this case, means if you consider this transistor circuit diagram, this is RC and then this is RB, VCC is connected and then this is grounded. Input is applied between this terminal and output is taken across a collector and a emitter. For this circuit, you have to replace this transistor with its equivalent circuits, means identifying the base, collector and emitter, and then replace a transistor with its equivalent model, means you have to write circuit, this is HIE, constant current source is HFE, IB, a base collector circuit. Means this transistor is written like this, or a equivalent circuit. Then you have to transfer that RC and RB in this circuit, where RC, that means you have to transferring this external component, means this is connecting to the ground, where at the low frequencies that capacitance is acting as a short circuit, and then this at a between the collector and a emitter you have to connect the resistance RC. The current flowing through this is IC and collector current flowing through this is I naught, and then here that resistance RB is also connecting between the base and a emitter, where you are applying the input voltage Vi, current flowing through this is II, output is taken across V naught. For this circuit, we need to determine, means analysis means we need to determine a input impedance ZB, Zi, a current voltage gain output impedance Z0, a current gain voltage gain AB and current gain AI. means we need to determine means that looking into the base emitter junction terminal, that input impedance is nothing but a ZB, and then looking into this, considering this external RB, this is Z denoted with a ZI, and then output impedance is to be considering this is Z0, by we are assuming that output impedance is open circuited, and then this resistance is Z0 dash. When you are looking into this a base emitter terminal, the only resistance is available is HI, hence that input impedance ZI is equal to HI. Because otherwise you are applying KVL, whatever the voltage applied here, the same voltage appears across this junction. If you open this circuit applying KVL, and then you are going to get the relation that ZI is equal, ZB is equal to HI, or ZB is equal to HI. By definition, this is nothing but VI by IB. And ZI is means after finding this ZB, you have to replace the entire circuit with its equivalent resistance ZB. Hence, this means you have to consider, we know that this resistance is RB, and then there is a resistance across the emitter and base, and the emitter is ZB. You are looking into this terminal, these two resistances are in parallel. Therefore, that is ZI equal to ZB is in parallel with RB. This is VI, current flowing through this is II. Current flowing through this is IB. Okay. Next, you have to calculate the output impedance. Output impedance means you are looking into the from the terminal collector and a emitter junction. For a collector and a emitter junction, that output impedance Z0, you are looking into this is nothing but V0 by I0 by definition, output current by output voltage by input current, with the condition is a Vi is equal to 0 set. When set Vi is equal to 0, then there is no current is to be flowing through this circuit. The Vi is 0, II is 0, IB is also 0. The constant current source HF into IB is becomes 0. Once this a current flowing through this junction is 0, this acting as a open circuit. When this open circuit, then its impedance Z0 is, when this open circuit means you are going to get that a infinite input impedance, that is equal to approximate analysis Z0 is equal to infinity. If you are consider a load resistance RC into the account, then Z0 dash equal to, means if you are looking into this side, means this entire circuit is replaced with Z0, and then this is RC. We are looking into this point Z0 dash, where Z0 dash is nothing but Z0 is in parallel with RC. Where Z0 is in parallel with RC, where Z0 is infinity, Z0 dash is equal to the applied external load resistance RC value. Next, we need to calculate on voltage gain. The voltage gain is defined as AV is equal to V0 by Vi. Because these two are parallel combination, there is no source resistance. Whatever the voltage applied, that same voltage to be appears across this terminal. Hence, that you are either there is no source resistance, therefore AVS is equal to AV. In this case, V0 is equal to, from this circuit analysis, V0 is equal to I0 into RC, where I0 is nothing but that current is to opposite to that of a collector current. Hence, this is equal to minus IC into RC, where this IC is nothing but HFE times IB. Therefore, this is equal to minus HFE IB into RC. Then by definition, that voltage is nothing, input voltage Vi is nothing but a voltage across the terminal base and a emitter. This is given by input impedance. By definition, Vi is equal to Zi into IB. If you take this ratio, then AB is equal to minus HFE IB RC divided by ZI IB. This will cancels. The voltage gain HFE is equal to voltage gain AB is equal to minus HFE RC divided by ZI. Means that voltage gain, this if you compare with respect to the RE model, that AB is also equal to the minus beta RC by ZI. This is also equal to the same. Or instead of ZI, we have to write this is ZB. Next is a current gain, another important parameter. Current gain AI is equal to I naught by II, where II and this is a parallel combination. I naught by II, already we know that what is I naught? I naught is nothing but minus IC. This minus IC is nothing but minus HFE times IB. Then AI is equal to minus HFE IB by II. Then what is this value? Where IB by II is nothing but a ratio of the base current to the input current at the input side. If you are looking into this circuit, if you redrawn, this is the resistance RB and then this is the resistance is ZB, current flowing through this is IB and then due to the input voltage current flowing through this is II. Means using this as transistor or a current of a 2-branch network, the IB is given by the total current II and opposite branch resistance RB divided by the total resistance RB plus ZB. If you substitute here, then the current gain AI is given by minus HFE times RB divided by RB plus ZB. If you are comparing this analysis with the exact analysis, the difference is the voltage gain AB is equal to AB into minus HFE RC by ZI. You are going to get only the difference is in case of one AI. Because if that RB is much greater than that ZB, then that A is approximately equal to, if RB is much greater than ZB, then AI is approximately equal to minus HFE. This minus HFE is nothing but a short circuit current gain of an transistor amplifier. Next, let us consider the voltage divider bias circuit. The analysis of voltage divider bias circuit is identical to a fixed bias circuit, where this in a voltage divider bias circuit, this is the circuit R1, R2, this is RE is in parallel with CE, and then that RC is connected to that a voltage, then that transistor input voltage connecting to the CC, output is to be taken across that collector. In this circuit at low frequencies, that capacitor means at this frequency, a small signal frequencies, that a reactance of a capacitor is very low, then this is acting as a capacitor is acting as a short circuit. If you consider this is acting as a short circuit, then this is connected directly to the ground. If you observe comparing this with respect to the previous circuit, then we can replace that RB by is equal to R1 is in parallel with R2. This, if you are replacing this RB is equal to R1 is in parallel with R2, then that analysis of the a voltage divider biasing circuit is identical to the a fixed bias circuit. Okay. Therefore, you are going to get wherever that R1 and R2 is there, RB, you are replacing this R1 and R2 with RB, and then you analyze, you are going to get back the same results where AB is equal to minus HFE RC by ZB and A is equal to minus HFE RB by ZB into ZB. There is no difference between the voltage divider biasing circuit and a fixed bias circuit. Next, let us consider a common collector amplifier or a emitter follower. Emitter follower. For an emitter follower means output is to be taken across the emitter resistance RE. Output is taken across this point, and then this circuit is used here also simple a fixed bias circuit VCC, where this collector is connecting to the directly connecting to the VCC, and then this is Vi. Why it is called emitter follower means whatever the input output voltage V0 is approximately equal to Vi. We need to prove this, the voltage gain of an amplifier emitter follower equal to 1, that is the objective. For this amplifier analysis, you have to replace this transistor from the wiring circuit with its equivalent, a simplified hybrid model. Then you are going to get the one way of analyzing this is a common collector configuration. This is HIC, or we can use a common emitter configuration on the base, a common collector configuration HIC, and then this is the current is IB, this is HFC IB, and then that output is to be taken across RE. This is your emitter, and then this is your collector. Because you are transferring this resistance means this is VCC is grounded, then RE is connecting between the emitter and a collector. Then that current flowing through in this direction, this current is IE, this current is I0. Output is to be taken across this point. Then to transferring this base means this is grounded means this RB is lies in between base and a collector. Then this RB is looking into this point. This is your RB. Input is applied at this point. When you are looking into this terminal, this is your ZB. When you are looking into this terminal, this is equal to ZI. When you are looking into this is a Z0, when you are considering that output resistance, this is Z0 dash. We need to determine that input impedance, output impedance, voltage gain and a current gain. This circuit is equivalent to the previous circuit. Then we got that input impedance ZB is equal to Vi by the base current IB. Then this value is equal to HIC. When looking into this terminal, this is equal to HIC. Already we know that the relationship between CC and CE, that CC is given by HI, C is equal to HIE, HRE is equal to minus of 1 plus HRE, HRC is equal to, and then HFE is equal to minus of 1 plus HFE, where HRE we are not using, you have to considering this. We know that HIC is equal to HIE and HFC is equal to minus of 1 plus HFE. From this circuit analysis, even if you use a common emitter amplifier, that ZB is equal to HIE only, and that ZI is equal to ZB is in parallel with RB. Output impedance you have to find. To finding an output impedance means you have to set Vi is equal to 0. When Vi is equal to 0, base current IB 0, this is acting as a open circuit, hence your Z0 is infinity. Then Z0 dash is equal to Z0 is in parallel with RE, this is equal to RE. Z naught dash is equal to RE, because this is acting as a open circuit. Next, a voltage gain AB. AB is equal to V naught by Vi. What is V naught? V naught, because this current emitter, because this is current flowing through, this is the, because this current is leaves, therefore you have to consider this IE. IE and I naught are in the same direction, therefore V naught is equal to I naught into RE. This is also equal to plus IE times RE. Then what is Vi? By definition, Vi is equal to that ZB into IB. Vi is equal to IB into ZB. This is, if you substitute the ratio, AB is equal to IE into RE divided by IB ZB, where IE is equal to HFSC times IB divided by RE divided by IB into ZB. This is equal to HFC RE divided by ZB. Then the voltage in AB is equal to, where HFC is equal to a minus of 1 plus HFE. If you substitute, this is a negative current, then minus into minus plus 1 plus HFE times RE by ZB. Next, we need to calculate the current gain. Current gain AI is equal to I naught by II, where I naught is equal to IE and IE is equal to I naught by II. This is equal to minus HFC IB by II. We need to find this, where HFC is nothing but, from this is nothing but 1 plus HFE times IB by II. To finding this IB by II, if the current flowing through this is II and then current flowing through this is IB, using this circuit analysis, we are going to get the IB is equal to a total current multiplied by a base resistance RB divided by RB plus HIC. Therefore, we are going to get from this circuit analysis, we will get this IB is equal to total current II into the opposite branch resistance RB and multiply with RB plus HIC. Hence, we are going to get a current gain A is equal to 1 plus HFE times RB divided by RB plus HI. If HI is much smaller than RB, means if that RB value is very large, then this denominator is approximately equal to RB, then AI is approximately equal to 1 plus HFE. This circuit provides a output gain. Current gain is equal to 1 plus HFE of a transistor, and then voltage gain AB is equal to 1 plus HFE times RE by ZB. If that ZB is large, a parallel combination, then this value is approximately equal to, gain is approximately equal to 1. This is about the an emitter follower. This can be also analyzed in alternatively. Instead of using a common collector configuration, this can be used, analyze this circuit by using a common emitter amplifier. Means you have to replace this transistor with the same circuit analysis, you have to replace the transistor with its equivalent model, then this is your base, this is HIE, this is your emitter, and then this is short circuited, this is equal to beta times IB and collector. This is current flowing through, this is your IC. Using this a common emitter amplifier, if you are transferring the external components, this emitter is connecting, instead of connecting ground, it is connecting, RE is connecting between the emitter and a ground. You have to first transfer this resistance RE. This is grounded. current flowing through this is IB and current flowing through this is nothing but IE, this is equal to 1 plus HFE times IB. This is grounded and then collector is connecting directly to the basis is grounded means connector is connecting directly to the ground and that RB is connecting between this point, input is applied this circuit. If you are analyzing this circuit and then you are going to looking into this terminal, you are going to get an input impedance ZB. When you are looking into this point, you are going to get the input impedance ZI. That output is to be taken across emitter and ground and then output is to be taken across this point. Where you have to considering this a resistance RE is a open short circuit and then you have to determine the output impedance Z0, input impedance Zi, a voltage gain and a current gain of a amplifier. This also gives the same results as derived earlier. Either you have to use analysis of a emitter follower by using this circuit or the earlier circuit. Apart from this circuit analysis, the emitter follower, it may be given any kind of circuits you are capable of analyzing a transistor amplifiers either using an hybrid model or a RE model and then you have to use appropriate model and then you have to find a solution. If we consider the same problem or a same example what we considered earlier, in this case that transistor amplifier shown in that figure uses a silicon transistor, VCC 24 volts, RC 1 kilo ohms, R1 is 100 kilo ohms, R2 10 kilo ohms, RE is 470 ohms. Then you need to determine the various current gain, voltage gain, input impedance and output impedance. Already we are calculated in the earlier session, we got AI is equal to 47 minus 47.7 and Zi is equal to 1077 ohms and Z0 is equal to 40.7 kilo ohms and Z0 dash is approximately 1.9 kilo ohms and AB is equal to approximately equal to minus 88.58. These are the values you are calculated by using an exact analysis. If the same problem if you solve by using an approximate analysis and then if you determine the error, that error should be less than 10%. Under what condition you are going to analyze an approximate analysis? Can you guess? Already we specified that HOE into RL should be less than 0.1. If where these two values are equal to or less than 0.1, then that error is less than 10%. For in this case, that HOE is given as 24 into 10 to the power of minus 6. This is 2 into 10 to the power of 3. RC is given as 1 kilo ohm. You are taken 2 kilo ohms. Please consider 2 kilo ohms for that example. This is equal to value is 48 into 10 to the power of minus 3. This value is 48 by 1000. This is equal to 0.048. This value is less than 0.1. Hence, that approximate analysis can be used and then error between the exact analysis and the approximate analysis not exceeds that 10%. According to this analysis, the current gain AI is equal to minus HFE. Means minus HFE means that HFE is given as 50. Now we have to determine the error between the exact analysis for this current gain, because using this current gain you are going to determine the voltage gain, input impedance and the output impedance. Therefore, if that error is less than 10% for the input impedance, correspondingly that error is for the other parameters also less than 10%. For this case, AI exact analysis is 47.7 minus 47.7 and a approximate analysis is minus 50, then error is defined as AI exact minus AI approximate divided by, you can take AI approximate. You have to take the absolute values, then this is equal to minus 47.7 minus into minus plus 50 divided by minus 50. This value is equal to 47.7 means 50 minus 47 is 3, 3 minus 0.7 is 2.3 divided by 50 into 100. This value is equal to 4.6%. If you use this an approximate analysis, that error between the exact analysis and exact analysis and approximate analysis not exceeding a 4.6%. For the other parameters are output input impedance Zi is equal to approximately equal to HIE. This is equal to 1100. If you are considering this ratio 1100 minus 1077 by 1100, that is just 33 by 1100, that error is less than a 0.3% or 3.3%. The voltage gain AV is equal to AI RC by Zi. This is equal to minus 50, AI is equal to minus 50 into RC is 2 into 10 to the power of 3 and Zi is approximately 1100. This is equal to approximately minus 100 by 11, you are going to get 90 minus 90.9. In this case, you got the value is 88.58. That output impedance Z0 is approximately equal to RC only. Okay. If you use approximate analysis, first you should be satisfying this condition. You have to verify this condition is satisfied or not. If this condition is satisfied, then that a approximate analysis is appreciable, and then this error is not exceeding a 10%. Summarizing this session, we discussed a small signal model of summarizing this session with, you have taken a complete analysis of a amplifier using an hybrid model and followed with an approximate analysis of an amplifier using a fixed bias circuit and a voltage divider bias circuit, and also you have discussed the emitter follower, and then you have to take an example on a complete analysis and an approximate analysis. You are shown that error between the exact analysis and approximate analysis always less than 10%. Thank you.